Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will use an R package to analyze data with a normal likelihood where both parameters, sigma squared, variance, and the mean are unknown. And we are going to be using independent Jeffreys priors for mu and sigma squared. Okay, let's begin. So this is the example that we're going to be doing here today. The random variable of interest is sweetness loss. Okay, and it's going to be computed as the difference between a score given before storage minus the score given after storage for a soft drink. Okay, so we have 10 observations. For instance, this one here, the first one here. So maybe the first taster, right? Maybe she assigned a 10 before storage, and then after storage, she tried the soft drink again, and she assigned an 8. So difference between 10 and 8, 2, right? And we have a similar situation for the remaining 9 observations. Okay, so what we want to do is use that data set to see if they provide evidence that the soft drink lost sweetness. Okay, so what we're going to be doing is we're going to be analyzing the average sweetness loss. Okay, so first, we're going to assume that these 10 numbers come from a normal distribution with unknown mean mu and unknown variance sigma squared. Okay, so we have these two unknown parameters. As we said, we are going to be using Jeffreys priors for both of them. So the prior for mu, well, Jeffreys prior for mu would be just proportional to the constant 1. Jeffreys prior for sigma squared would be just the reciprocal of sigma squared, 1 over sigma squared, right? So since we're assuming that they are independent, the joint prior for mu and sigma squared would be the product of those two priors, 1 times 1 over sigma squared. We end up with 1 over sigma squared, right? So when we consider a normal likelihood with unknown parameters mu and sigma squared, and we use this prior, right, we showed in another video that the posterior distribution for mu happens to be proportional to a t-distribution with n minus 1 degrees of freedom, right? Remember, we did that derivation in detail, okay, in another video. Okay, so now let's try to analyze this data. First, we're going to do things by hand, and then we're going to compare with the results that you get using an R package. Okay, so here we go. Let's launch R. And maybe since we're going to be doing things by hand first, and then we're going to compare with the R package, let's set this up, right? So first, mu represents the average sweetness loss, average sweetness loss. Okay, what else? We know that the hypothesis that we want to test is whether or not, right, that average is positive, right? Because what we want to see is if these numbers were higher before the ratings that the soft drink got before storage were higher before storage than after, right? So we want to see if the average for these differences is positive. So our null and alternative hypotheses look like this. It would be mu is greater than 0. That's what we would like to show. So we're going to place it here on the alternative, that mu is greater than 0, and the null will be the complement of that event. Okay, less than or equal to 0. Okay, so that would be our step 1. Step 2, we need to find the posterior probability of H0, right? But what we know from what we did in our derivation is that the posterior probability of mu given our data is proportional to the it's proportional to a t distribution with n-1 degrees of freedom, right? So to go from mu to t, we used a transformation. Let me remind you what transformation looks like. And what we also mentioned at some point is that that transformation is helping you to go from a non-standard t distribution to a standard t distribution. So what we have here is mu minus, and let me call it y bar, divided by the standard deviation of y bar divided by the square root of n. Okay, makes sense? Okay, so what we want, right, is we want to find the posterior probability of the null hypothesis. So meaning that probability given the data. Okay, so what we know is that what we have to do is we have to standardize, because then we're going to be able to use tables or, you know, R functions that have to do with a standard t. Okay, so let us standardize that guy using our transformation. So on the left hand side of that inequality, I'm going to be doing it with symbols. On the right hand side, I'm going to be doing it with numbers, and that's why we're going to need R, right? Because I will need to find the sample mean and the sample standard deviation for that data set. Okay, so first let me go back here. Let me see if I can copy paste this guy. So let me call it sweetness loss. We don't want this one here. Okay, so just to check that everything is fine. There we are. Those are our 10 observations. Okay, so we need y bar, the average for those 10 observations. We need the standard deviation. Okay, so now let me plug in here. So we have 1.02 for the average, we have for the sample mean or average, and we have 1.1961 roughly for the sample standard deviation. So we have something like this, mu, which, by the way, here we have a 0 on the right hand side, minus 1.02 divided by, and we have 1.1961 0.05, okay, divided by the square root of n. In this case, 10 observations. Right? So now, by using that transformation, this guy, we know, has a t-distribution with 9 degrees of freedom. So we have t-distribution with degrees of freedom 9, less than or equal to something. Let's find the something here. Okay, so what we need is this guy here, mean, but with a negative sign. So we need -1 times this divided by the standard deviation divided by the square root of our sample size, which is 10. Okay, so that's our number on the right hand side of that inequality. So now all we have to do is to find the area to the left of -2.69 for a t-distribution with 9 degrees of freedom. How do we do that? Easily. Just use the pt function, right? We need this guy here. So what we need, right? Well, what we're doing there is we're evaluating the CDF of a t-distribution with 9 degrees of freedom, right? So the posterior probability of our null hypothesis happens to be 0.0122 roughly. Okay, so if, for instance, we were using a 5% significance level, then since that posterior probability is less than 5%, we would reject the null hypothesis. Clearly, the alternative is more likely, right? And okay, so we reject the null hypothesis. It makes more sense that there's a positive sweetness loss. That's more likely. Remember that the posterior probability for the alternative is going to be the complement of that. So 98 point something%. That would be the posterior probability for the alternative. Okay? Okay. Now, let's compare what we would get if we used an R package. Okay? So we're going to be using the following package, which I am assuming you already downloaded and installed. Okay, Bolstat. Now, the function that we want to use is base.ttest. Okay, there we are. So if you want to learn more about that function, this is what you do. Just type help and then brackets base.t.test, and you'll see the syntax of the function, right? So first, we want to, in this case, carry out a hypothesis, a Bayesian hypothesis test. So in this case, you could have 2 samples. We only have 1. So we would need this argument here. Alternative, as you can imagine, we have the 3 choices: 2-sided, less than, and greater than, the 2 choices for one-sided alternatives. Mu equals 0 represents this, the value here for the null, right? Okay. Let's continue. So what else we have here? Prior. This is what we need. We're going to be using Jeffrey's prior, and yeah, so basically that's the information that we need. Here we go. So base.t_test, don't need this anymore, and then we have sweetness loss. We have the alternative. In this case, right, the alternative is greater. What else we want? We want the value for the mean that defines here the null. So the default is 0, but let's be super specific, mu less than or equal to 0. And then we have our prior, which is going to be Jeffrey's prior. And there we are. Let's take a look at that output. So as you can see, what they report here as the p-value, what they mean is the posterior probability for H naught. Okay? Now, what they have here, that t is just the absolute value of that transformation. Okay? And then, well, that's it. Right? This guy, as you can see, 1.02 is just the sample mean. Okay? Now, one more thing. Say that, okay, now that you have carried out your hypothesis test, you conclude that there's a positive sweetness loss, right? But now you want to estimate that average sweetness loss. So the next step would be finding a credible interval. So let's find a 95% credible interval for mu, the average sweetness loss. So doing this using that function base.t.test is really simple. Okay, so let me show you what we need. What we need is our data. We already have it, sweetness loss. There's no need for an alternative if we want a credible interval. There's no need for a value for mu under the null hypothesis. Jeffrey's prior, good. And then, since we want a 95% credible interval, what we need is that argument conf level. Okay, but in this case it's a probability level, right? So that's our 95% credible interval. Okay, for this guy. You can try and find it by hand, and you'll see that you will end up with something like this. Okay, make sense? Okay, so let's summarize what we did here together. So we had some data set, right, and we wanted to first carry out a Bayesian hypothesis test for the mean, assuming that we were dealing with normal likelihood where both mu and sigma squared were unknown. Okay, so to do so, we did it by hand first to understand what the output means for this function from the R package pulse that is doing. And the function that we're going to be using is base.t.test to carry out that Bayesian t-test, if you will. Okay, so that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.